Past couple of lessons we've been talking about exponential growth functions, and today we're going to talk about exponential decay functions. Now, with exponential growth, as each input went up one, we were multiplying by something as we went to the right, dividing by something as we go to the left, and so we would get a curve that looked kind of like this. With exponential decay, it's the exact opposite. As we go to the left, we multiply by something, and as we go to the right, we divide by something, getting smaller and smaller. So instead of growing along this curve, we are going to shrink. We're going to decay, like so. So the format looks very similar. It's still y equals a times b to the x. The difference is that b is going to be between 0 and 1 instead of being greater than 1. That's how we'll identify it as decay. So if we're given a set of values, a table, we can identify whether it's exponential and whether it's growth or decay very quickly. If we start with a set of inputs like so, and the outputs, we first check to make sure that all of our y's are going, or all of our x's are going up by the same each time, which they are. Each one is going up by 1. Then we evaluate the y's. Are they going up by a multiple each time? Well, 1/9 times 3 is 1/3. 1/3 times 3 is 1, and 1 times 3 is 3. So this is exponential growth with a base of 3 and our starting value when x is 0 of 1/3. That would be our equation, and it's growth because b is greater than 1. Now, if I had a table that looked like this, again, we check to make sure that our x values are going up by the same amount each time, which they are. They're going up by 1. I look at my outputs. Now we can look at this two ways. As we increase, we are dividing by 4 each time. 4 divided by 1 is 4. 1 divided by 4 is 1/4. And 1/4 divided by 4 is 1/16. Or we could look at it as multiplying by a number smaller than 1. 4 times 1/4 is 1. 1 times 1/4 is 1/4. And 1/4 times 1/4 is 1/16. And so we can look at it the same way we look at our growth functions, where 1/4 is our base. And our initial value when x is 0, y is 1. So there's our function. And it's decay because b is between 0 and 1. 1/4 is bigger than 0, but smaller than 1. So that's how we identify and come up with a function for exponential decay based on a table. Now, let's graph an exponential decay function and determine its domain and range. So the function we're going to work with is y equals 1/2 to the x. The first thing we need to figure out is what our initial value is, what our y is. Now, since it just starts with y equals 1/2 to the x power, and we don't have another a number there in the front, then a is just 1. That's our starting value. Okay, so still when x is 0, y is 1. That part hasn't changed. Now what's changed is as we go to the right, we're multiplying by 1/2 instead of as we go to the left. Okay, so we go from 1 to 1/2 to 1/4 to 1/8 and so on. As we go to the left, we divide by 1/2, which is the same as multiplying by 2. And so we go from 1 up to 2, 2 up to 4, 4 to 8, 8 to 16, and so on. And so we get a function that starts very high on the left side of the graph and decays. Now, if you think about it, this is just a horizontal reflection, or a reflection over the y-axis of our growth function. Growth function normally would look like this. So we have here a function that's been reflected over the y-axis. It's just a little bit of a switch around. So it's going down when it normally went up, and it's going up when it normally went down. Now, what about our domain? Has our set of inputs changed from our exponential growth functions? It hasn't. It's still all real numbers. What about our range? Well, again, we're not able to go down to or go down below or even hit 0. So we want all of our positive real numbers, because there's no exponent that I can raise 1/2 to and get a negative number or even 0. So our output is all positive real numbers. Why don't you try one of these? Y equals 0.4 to the x. Pause the video, give it a shot, and see what you come up with, and I'll pause the video and we'll go over it together. So again, we have a graph that starts at 1 because our a is 1. There's no extra starting value there. As we go to the right, we're going to multiply by 0.4, but it might be helpful to rewrite this as a fraction, which is 4/10 or 2/5. So we're multiplying by 2/5 as we go to the right. So we go from 1 to 2/5 to 4/25, and so on. As we go to the left, we're dividing by 0.4 or 2/5, which is the same as multiplying by the reciprocal, 5/2. So we go from 1 to 2.5, or 5/2, to 25/4, which is actually 6¼ So when I plug in that 2, I'm multiplying by 5/2 twice, which is 25/4, or 6¼ So that gives me an idea of where my next point should be. Right about here. The next point would be 125/8, which is which is a little larger, I think, than we have room for on the graph. 125/8 is equal to 15 5/8. We don't quite have that room on our graph. So we know it's going to be way up there. It's just kind of a guideline for our graph. And there we go. And we're looking at the same domain and range as the last one. Again, we can plug in all real numbers, but we're only going to get out, for our range, positive real numbers. So that's the first half of exponential decay. If you have any questions, feel free to ask. If not, you can move on to your homework.